You good to go?
Fine.
You're good to go? Yeah. Okay, so let me introduce today's speaker for the FPGA seminar. It is Rafat Rashid. He will be talking about comparing an overlay to other ways of computing things. Take it away.
Hello everyone, thank you for coming. My name is Rafat Rashid. Today I'll be presenting our paper on comparing the efficiency of the tilt overlay processor with Altera's OpenCL HLS. FPGAs are a more difficult design target compared to other platforms such as CPUs or GPUs. First, the cycle-accurate hardware description required to program FPGAs is both difficult and time-consuming to write. Second is due to the long hard compile times, taking up to a day for a large design, compared to seconds or minutes for the software alternative. Thus, there is great interest in programming FPGAs with high-level languages to alleviate these bottlenecks. What are some of these options? Option one is to use high-level synthesis tools that translates high-level languages such as C into custom hardware. Examples include Altera's new HLS tool, which uses OpenCL as its programming language. However, HLS tools still suffer from long hard compile times, with the software kernel requiring resynthesis after every kernel code change. Alternatively, we can use overlays which maps the same software kernel onto a software-programmable hardware. Unlike HLS, overlays need to be synthesized once and then can quickly be reprogrammed. This also means that overlays are versatile, supporting multiple software functions for the same engine. However, this has an area overhead associated with it. Our specific focus is working with a data path that is both application customizable as well as software programmable. And for this data path, ideally, we want to achieve high throughput per area, or be computationally dense. We assume thread data parallelism and target floating point applications, and the result is the tilt overlay processor, which was prior work completed by Artujob and Tilly. This is the standard tilt architecture. Tilt comprises an array of functional units connected to a scratchpad multiported memory via crossbars. Tilt supports both thread and instruction level parallelism and is highly configurable with a customizable FUMX and memory architecture. Tilt is designed to have minimal hardware. It executes very long instruction words or VLIW instructions, which are statically scheduled by an offline software compiler, and stores these instructions in a small unchecked memory. The tilt compilation flow comprises two parallel flows. The software flow is fast and takes the application and generates the tilt instruction schedule onto the target tilt architecture. And the hardware flow is slow and synthesizes that architecture onto the FPGA. On subsequent kernel changes, ideally we only need to go through the fast software flow to regenerate the contents of the instruction memory and reprogram the overlay. In contrast, the synthesis step needs to happen once. Our specific contributions include designing a memory fetcher unit that interfaces multiple tilt compute cores with off-chip memory. We will also propose several architectural enhancements to tilt to improve the efficiency of large loops and of indirect memory access. Further, we propose a software predictor tool that can rapidly select the best tilt and fetcher design configuration for a target application without requiring manual design effort. Finally, we perform a thorough efficiency comparison of our application-tuned tilt system architectures with custom designs produced by Altera's HLS tool. We begin by a brief description of the memory fetcher, which is a configurable and scalable off-chip data prefetcher and a coprocessor to tilt. Like the tilt compute init, it is designed to have minimal hardware, which means that it is also statically scheduled. The instructions that move data between multiple tilt compute cores and off-chip memory is separated into two parallel instruction streams. To illustrate with an example, input data is read from DDR memory into these FIFOs using the fetcher's instruction stream. At some later point, this data is written into the tilt data memories using the tilt's execution stream. Multiple tilt compute cores then compute on the data to produce output results, which is then written back into the outgoing FIFOs of the fetcher using the same tilt execution stream. Finally, at some later point, this data is written into DDR memory using the fetcher's execution stream. Communication with DDR memory has variable and long memory access latencies, which is not always predictable, and data is accessed in bursts to maximize DDR bandwidth. In contrast, communication with the tilt cores has constant, fast, and deterministic access latency. The intermediate FIFOs decouple the high compute rate of the tilt cores from the inherent indeterminism and long latencies associated with off-chip communication. The entire component with multiple tilt cores connected to the fetcher is called the tilt system. I'll now briefly describe some of the enhancements, optional enhancements that we have added to tilt to better target specific application types and to produce more efficient tilt designs. One of these optional enhancements is the support for loops within the compute kernel. With the basic standard tilt core, loops need to be manually and fully unrolled. This can produce denser schedules and therefore higher throughput because loop iterations can be overlapped, but also require significantly more instruction storage. We have implemented a small loop init FU that allows tilt to execute a section of a schedule multiple times. This means that the body of the loop does not need to be unrolled and can be scheduled once. The loop unit FU, when it is added, costs only 9.8 ALMs. To illustrate how it works, this is an example tilt schedule containing a loop. The loop start operation at the beginning of the loop sets the number of loop iterations, and upon reaching the end of the loop, that value is decremented by 1. When that value reaches 0, we exit the loop, otherwise we re-execute the body of the loop. Another enhancement is the shift register addressing mode that was motivated by the 64-tap filter, which is one of our benchmarks. This filter is most efficiently implemented as a fully spatial compute pipeline, as illustrated by this figure, with input or output data placed inside shift registers. So how do we efficiently implement FIR on tilt? So tilt is statically scheduled. This means that these addresses in the tilt schedule must be known at compile time, and that on subsequent iteration of the tilt schedule, the same data memory locations will be accessed. So we can naively implement FIR on tilt with extra FU operations that reads the memory location and writes that data item to the adjacent memory location, essentially shifting the data as illustrated by this figure. However, this results in a longer tilt schedule than necessary, and it's not very efficient. Alternatively, with the shift register addressing mode, a small amount of additional hardware is generated that allows FUs to access adjacent memory locations on subsequent iterations of the tilt schedule, thus essentially removing the need for the extra shift operation. This is accomplished with this offset by adding an offset to these static addresses in the tilt schedule. The result is much better throughput and a smaller instruction memory at a cost of 54 LNs for this extra hardware. Now, most real-world applications may also have some dynamic memory access behavior, and as you have seen, this is not supported by the standard tilt architecture. We have also, we have also added full indirect addressing support capability into tilt. When this optional feature is added, data stored in the tilt data memories may be used as memory addresses instead of the static addresses in the tilt schedule. So the hardware cost is 97 ALMs for 10-bit addresses, which is most typical for area-efficient designs. Now, the main takeaway of the last few slides is to emphasize that the tilt overlay can be optimized to target specific application types with these enhancements. Now, as mentioned, both the tilt and fetcher components are highly configurable. In this illustration of a single tilt compute core, we have multiple functional units connected to tilt's data memory, composed of several memory banks, each with a single thread. First, we can vary the FU mix. With a total of 9 FU types and the capacity to have multiple instances of each, numerous FU mixes are possible. For the data memory, we can vary the number of threads, for example, with deeper banks, or increase the number of memory banks for more thread-level parallelism. Further, we can increase the number of read and write ports per memory bank, which allows us to issue more operations per cycle. But this will be at the cost of bigger memories and bigger crossbars. Similarly, for the fetcher, we can connect multiple tilt compute cores in parallel. We can vary the data FIFO depths to prefetch more or less data. And we can vary the extra number of external read and write ports, which determines the number of off-chip data words that can be accessed by the tilt cores in parallel. Taken together, this constitutes a very large design space. We want to achieve high throughput per area, but the best tilt and fetcher configuration can be different for different benchmarks, thus making it difficult for the designer to find the best design solution for a given application. We have developed a software tool to automate this process of finding the best architectural solution for a target application. The tool uses software performance and area models instead of requiring hardware synthesis, and a heuristic-based prediction algorithm to intelligently prune the design space that it explores. The end result is that we have an application customizable, software-programmable overlay architecture with an automated tool that can quickly select the best design solution for a target application without requiring manual designer effort. I will now present the evaluation of the TIL system and our comparison with the Altera's HLS tool. Recent prior work completed by Chen and Singh have demonstrated that Altera's OpenCL HLS tool produces high throughput, power efficient designs on FPGAs compared to CPUs and GPUs. We perform a thorough efficiency comparison of our enhanced application-tuned TIL system architectures with custom designs produced by Altera's HLS tool. For our benchmarks, we use data parallel, compute-intensive, floating-point applications from a variety of application domains. Examples include image processing with HDR and mathematical applications such as the Mandelbrot and the 64-Tapfer filter. For our evaluation platform, we used an Altec D5 board containing a SHREX5 FPGA and DDR3 memory. For evaluation metrics, we measure compute throughput in millions of tasks completed per second, where a task is a single instance of a compute kernel. We measure FPGA area in the amount of silicon area that is consumed by our designs in units of equivalent ALMs, where other resources on the device, such as block RAMs or DSPs, are also converted into that unit. Finally, we compare and rank our designs using the compute density metric, which is simply a ratio of throughput per area. For a comparison methodology, we assume all input data initially resides in DDR3 memory and implement tuned compute kernels for either approach. For the TIL system architectures, we use the predictor to select the best configuration, and throughput is obtained through cycle accuracy simulations in MALSIM. For a fair comparison, we exclude host-to-accelerator data transfer times and execute as many threads as necessary to saturate throughput. This graph shows the normalized compute densities of the TIL system designs to that of OpenCL HLS. We observe good performance, between 41 to 80% of the compute densities achieved by the OpenCL HLS designs. Here we summarize the improvements in tilt efficiency due to the enhancements that we have described earlier. The Mandelbrot compute kernel features a loop that iterates up to 1,000 times. With the addition of the small loop unit FU, we obtain a 6x improvement in compute density due to scheduling a single iteration of the loop. And as mentioned before, the 64-Tapfer filter is implemented with the shift register addressing mode. We obtain a 3x improvement in compute density due to the removal of the extra data shift operations, and at an additional cost of only 54 ALMs. We also observe a compelling gain in productivity. The initial setup of the TIL system requires a software compilation of the application kernel using the predictor to select the densest tilt and fetcher configuration and synthesizing that architecture onto the FPGA, which takes 29 minutes on average for our benchmarks. This is compared to 103 minutes for our OpenCL HLS designs. On subsequent kernel changes, we need to regenerate the contents of the instruction memories and reprogram the overlay, which takes 38 seconds on average and can barely be seen on this graph. This is 163 times faster than OpenCL synthesis. The runtime over predictor tool is 55 seconds. This tool enables fast selection of the tuned TIL system architecture without requiring manual designer effort. Architectures also need to be scalable to meet compute requirements and/or area budget that is either set by the designer or the system environment. We scale our TIL system by executing multiple TIL compute cores in parallel. And similarly, we scale our OpenCL HLS designs by replicating the compute pipeline. This graph shows the throughput scaling results for the Hodgkin-Huxley benchmark. We observe near linear scaling in throughput and area for our TIL system designs as we scale our design from 1 TIL core up to 20, but it is less than that of the OpenCL HLS. There are a lot more intermediate design solutions available to the TIL system, and it can also scale down to much smaller area-efficient implementations. As mentioned before, the 64-Tapfer filter is normally implemented as a fully spatial compute pipeline, as illustrated by this figure. This implementation achieves very good performance for relatively low area on OpenCL HLS. However, if such a high throughput is not required, we may wish to scale down our design to save area. In this illustration, we have a single compute unit, or DSP, performing the same 64-Tapfer computation. The throughput achieved is very small, and we do not save that much area due to the large muxes which are required at the inputs. With 2 compute units, require smaller muxes at the inputs, but you have 2 sets of them, and there is additional muxing required to forward the output of one compute unit to another. The throughput is slightly better, but is still insufficient. Between 4 and 32 stages, the muxing overhead grows or increases with the number of compute units, resulting in an overall growth in area, with the design consuming 86% of the chip's ALMs at 32 stages. We conclude that OpenCL HLS has difficulty producing area-efficient lower throughput systems for spatially pipelined computations. Here we have the same graph, but the tilt system scaling results are plotted as well. We observe linear scaling in throughput and area for up to 70% of the chip's ALMs. We are also able to exceed the throughput of the spatial OpenCL FIR design with about 70 tilt cores, but at a cost of 2 times the area. The tilt system enables small area-efficient designs with modest throughput and is also capable of exploring throughput and area regions that OpenCL HLS cannot reach. And as you have shown, OpenCL HLS cannot efficiently scale down spatially pipelined computations. So to summarize, we have designed a configurable and scalable memory fetcher unit that is capable of moving data between off-chip memory and the multiple tilt compute cores, and is a loosely coupled coprocessor to tilt. We also propose several architecture enhancements to tilt to improve the efficiency of large loops and of indirect memory access. Further, we propose a software predictor tool that can rapidly select the densest tilt and fetcher configuration without requiring manual designer effort, thus improving designer productivity. Finally, we compare our enhanced and application-tuned tilt system overlay architectures with custom designs produced by Altera's HLS tool. We find that our tilt system has fast application recompile times and also has reasonable but lower throughput versus the sweet spot OpenCL architectures. Further, the tilt system designs presents a wider trade-off range of throughput versus area solutions to that of OpenCL HLS. Therefore, we conclude that the tilt system paradigm is an useful complement to OpenCL HLS. Thank you very much.
So how do you load Trojan data onto your overlay architecture? Through PCI Express or what?
So we do not do the PCI Express. We load it into an instruction memory.
So it's just loaded as a MIF file into your
Yes,
engine.
exactly.
Did you take that into account when comparing versus the OpenCL generated system? Because they have to,
Yeah.
both the compile time, they have the PCIe core to synthesize, and
Yes.
and area-wise as well.
Yeah. So for the area component, we measured the memory subsystem and the compute kernel, and we've taken that into account when we taken to measure the area.
Okay.
And for loading onto the PCI and transfer between host to kernel, or to the FPGA rather, we didn't take that into account. So in our comparison methodology, we mentioned how we do not account for the host to accelerator transfer times. We assume all input data initially resides in DDR3 memory. Same thing for the tilt system, so we can have a fair apples-to-apples comparison between the two.
Cool. So basically, you just compare the compute part and the off-chip memory
Yes.
systems.
Yeah.
What about? So you mentioned just ALMs for your area. Is there a big if you have?
No,
is
it's
there a
not
big
just
discrepancy?
ALMs. It's equivalent ALMs. So we convert. So we measure the layout area. So other resources on the device, such as block RAMs and DSPs, will be converted into equivalent ALMs in layout size.
But is there a big discrepancy in ratio between between resource usage types between your system and PCI Express? Like, do you use significantly more DSPs or RAM blocks than pure logic?
Versus are you
Versus
talking about tilt
OpenCL,
system
yes.
versus OpenCL HLS,
Yeah.
or just OpenCL HLS and PCI versus compute?
No, not PCI. Just the compute and off-chip memory subsystems of both PCI, OpenCL and tilt.
Oh, okay.
Are the ratios of resource usage types significantly different between OpenCL and tilt?
Yes. The reason for that is because for the tilt system, we try to have a area function units that we want to reuse. For the OpenCL, it says lays it out as a fully spatial compute pipeline to improve throughput. So we do see a lot of DSPs compared to tilt, where tilt uses much fewer DSPs. Yep. Go ahead.
Can you go back to that chart of all the different sizes for the OpenCL?
All the different
They had like the 1 to 64 taps, OpenCL performance and area. I want you to re-explain why the 32 tap version is like twice as big and like a quarter as fast.
I do not show the 32 tap.
Oh no, it was near the end of the presentation. You put your line like in between it, and you said that you are good at
Oh,
flow.
that one. Okay.
Yeah.
This one, for example.
This one?
Yeah.
One back.
Or yes. Yeah. So can you just explain this graph to me, because I'm not following.
Perfectly
what's
blow it up
happening.
so it's more visible.
Yeah.
Just go full screen.
Let me do it. It's nice.
It's Mac. Slash. Okay. So.
Right. So this is like the 32 tap version is 3.5
So this is
times
the-
bigger, and it's half as fast.
So this is probably did not explain it properly, but this is performing. So for this example, we have 2 compute units, but it's actually performing the same 64 tap for computation. So it's not. This is not an example of a 2-tap computation. The reason you need muxes in the front is because you want to select between the filter coefficients and the inputs that you want for that 64 tap for computation.
Okay. So the numbers on the graph 1, 2, 4, 8, 6. That is the number.
Those are the
of-
number of compute units. No, those are not the number of taps. Does that make
Okay.
sense?
Sort of. Okay.
So with 64 stages, you don't need any muxes.
No.
Okay.
But otherwise, you do need muxes because you're doing a 64 tap computation on fewer computers.
Okay.
Fewer compute resources. So that was the main point of this graph. Go ahead.
So if you were to integrate this with OpenCL HLS, so you said it's a useful adjunct to OpenCL HLS, what would you have to change and what would the upside be?
So what we essentially, there wouldn't be, I don't think, significant changes to the OpenCL, what the OpenCL compiler actually does, but it will be essentially seen as an IP block, right? And tilt, the main uses of this would be if there's a coarse computation that needs to happen, you can offload that onto tilt. Tilt will compute that. The main advantage of using the tilt overlay as opposed to a fully spatial compute pipeline is that it will use significantly less compute resources to perform that computation. The throughput will be also a little bit smaller because of that as well. But the main advantage of using the tilt overlay as opposed to, let's say, a compute pipeline or a custom design is to reuse the compute resources on the FPGA device. Does that sufficiently answer your question?
I think so. So basically you're saying
Okay.
like if you don't need that much throughput, you think with the program model is close enough, you could integrate it into OpenCL and just have it target it when it doesn't need full throughput
Yes.
and save the area.
Yes. Yes.
Another, that makes sense to me. I mean, another, so kind of just leading discussion here, because we've talked about some of these things before.
Okay.
Another interesting thing that clearly you could do is leverage your compile time advantage to allow prototyping of an OpenCL
Yes.
system.
Onto an overlay architecture. Which is
And recently,
Altera is doing that as
very
well.
recently, so
Yeah.
Altera is actually doing that with a
Yes.
different kind of overlay. So I don't know if you have any thoughts on what kind of overlay they're using and how you would contrast what you're doing.
No, I haven't looked into too much about that, but yeah, you told me this on our dry run as well, and yeah.
Okay.
Go ahead.
Quick question. I mean, one of the things with OpenCL is you need to necessarily copy the data to sort of memory so you can operate on it.
Sure. Yeah.
So to me, that's an extra copy and not necessarily that efficient for, say, streaming behaviors. So, for example,
So are you
if
just talking about copying from host to
Yes, yeah.
object?
So that has to be a necessary step in
Yes, it
OpenCL
is.
in order to use the data.
Mhm.
So that's an extra copy.
Mhm.
So I'm just wondering if the tilt architecture or what kind of changes would you have to do to process streaming data, say coming from either PCIe or Ethernet or any other streaming source of data without having to go to memory first. Is that
So we actually assumed the same kind of paradigm as OpenCL in that regard. So when we did this comparison, we strictly assumed that all input data initially resides in off-chip data memory, off-chip DDR memory, and everything else, the streaming from PCI to DDR memory is exactly the same as OpenCL HLS, not different from, we do not do anything differently or novel in that regard.
I guess my question was, how hard would it be to change it so that it doesn't have to do that?
doesn't have to do that extra copy.
Yeah, it doesn't have to process it as it comes.
Comes from where exactly? It needs to come
so you
from.
have a network, a 40 gigabit network interface, and you're going to process the data as it comes without having to put it into memory first.
Onto the host first.
No, directly from the FPGA. So you have,
Okay.
you have a network adapter into the FPGA.
Okay, so you
into
just
the
ignore the
FPGA.
DDR.
Yeah, just
Yeah. Again, we do not need to significantly change too much, I don't think, for the tilt architecture, because you essentially, instead of connecting the memory interface to DDR memory, you connect it to whatever other streaming system that it's coming from. And the way it's set up, if I can go back, is a bunch of so instead of connecting to these channels, or these FIFO channels into DDR memory, you connect it to PCIe or some other external source. So there wouldn't be any significant difference in the actual architecture, because you essentially need to buffer or prefetch the data into the FIFOs anyways to improve the latencies to the object source. Go ahead.
Could you go back to the loop unit? It's
Sure.
a little bit before that. Just wanna- Quite get what it was. I know what loop unrolling is, but it's just a little bit of hardware. What is it that you did, and you talked about the fact that
Yeah, this doesn't actually show the architecture of the loop unit and go into scheduling details and all those things. So that's a little bit out of context from what was actually in the paper. But I can go over it a little bit if you want.
Yeah, I just wanted to know what it is, the
Okay.
loop unit, and is its core contribution that you didn't have to start replicating the instruction memory? Is that what you
Yes,
said?
the instruction set. Yeah, the instructions in the loop body.
So you
do
don't
not
have to do that. You just
no.
keep sort of. What do you do?
So instead of so the other one of the other.
Is you just
I think I pressed stop.
it's okay. Just press it again.
Oh, okay. Interesting. So what we traditionally did was to unroll the loop. In that case, what that meant is that the loop body would need to be, there will be separate set of instructions for each iteration of the loop. And therefore, we can also, if there are no data dependencies between these loop iterations, we can also schedule them together, thus producing a denser schedule. However, because we're scheduling a separate set of instructions for each loop iteration, it also grows the length of the tilt schedule as well, thus requiring much more significantly larger instruction memory as well. So what this does is schedules the loop body only once, and then at the end of the pipeline, the instructions drain, right? The pipeline gets drained, and then we go back to the top and execute the loop body again, the loop body instructions again, on different data. So that's essentially how this works. And the loop body, so the loop unit FU simply has a register that keeps track of how many times that loop is iterated.
So this sounds like a decrement and conditional branch.
Mm-hmm.
Do you have other types of branches?
We do support branching. We didn't talk about this here, but we support branching through predication.
Okay, so that's not branching, that's predication.
Yes.
Okay.
Yeah.
So this is the only branch instruction you have?
Yes. I don't want to confuse and say no, we do not support branch. It's just through predication.
Which is not a branch.
Yeah.
It is to conditionally compute
Yes.
things, but it is not a branch in that it changes the flow of the
Yes.
program.
Yes.
So it's a straight line program except for your loop instruction.
Mm-hmm. Go ahead.
Because you don't unroll the loops, do you are the schedules a lot less efficient because of it? Like how much less efficient because you don't unroll the loops?
I can't remember the exact number, but I think it was a 20% or so drop in throughput. Is that right? Maybe. Yeah, it's about around 20% or so, I think. On average. Go ahead.
So you've gone through 5 applications and you added 2 custom units.
Mhm.
Well, you added 3, but I think 2 were motivated by
Mhm.
specific applications.
Mhm.
So if you do another 5 applications,
Mhm.
do you think you need another 2 custom units, or do you think you've got most of the things you would need there?
I think we've got most of the things you need.
You were comparing to Altera OpenCL, and you're saying how it's spatially computing. I haven't used OpenCL. There's at least one OpenCL person here, creative person here.
Okay.
There's got to be a knob that changes the amount of space consumed.
There is a knob. So there, for example, you can change the unroll factors. So in your software code, you can change the unroll factor in how many times that body will be unrolled, right?
And that changes the amount of
and
space,
changes the amount
used
of compute resource that are actually used. And that's how I produce the FIR results. But the main point is that OpenCL, the compiler can do it. It just doesn't do it as efficiently as the full compute pipeline version.
So it doesn't do what is efficient?
So the smaller, lower throughput systems, it doesn't produce as computationally dense or area efficient designs as the fully unrolled versions.
So maybe you could explain why. Like why, I know you talked about it briefly in the slides, but maybe like why does that happen?
So part of it has to do, this is a little bit more going into specifics about the actual implementation and things like that. But part of it has to do with, so there's a compute pipeline, and there are FIFOs and memories in front of it, and the FIFOs essentially stream the data into the compute pipeline. And how you obtain high throughput is so that you are able to prefetch enough data into your FIFOs such that you can stream it into your compute pipeline, and at each cycle you're doing something useful, right? But if you do not allow for your OpenCL compiler to do that, then you're significantly reducing the amount of throughput that you can achieve. Because you might, for example, turn a knob so that you do a bunch of things in a single compute cycle, right? Or you reduce the number of compute pipelines so that it essentially has to reuse those same resources at different cycles, right? And that's kind of what I've alluded to with the FIR computation, where we have performed the same 64-tap FIR computation, but with fewer DSPs. And what do we end up because of that?
So what further ideas you have after this?
So further ideas, one thing I would like to do is, the predictor is a pretty interesting solution where you have an overlay architecture which is not only software programmable, where you can have multiple application kernels mapped onto the same overlay architecture, but we also are able to tune it to a specific application. And in the beginning, most of that tuning process had to be done manually. But with the predictor tool, we're able to do it in an automated fashion, but for a specific application. So the next step for that would be to tune it to a group of applications. So you have a group of application with similar compute or memory characteristics, and it is a similar set of functional units or functional unit types. And how do you map this overlay architecture to a group of applications? Let's say 5 sets of applications, and you put it into your compiler, and the compiler automatically figures out the best architecture solution for it. So that's one thing. Another interesting thing is, one thing that Professor Betz alluded to was how to integrate the tilt processor, or the tilt core, which is, its main point is to be small, area efficient, and to essentially reuse the aerial functional units that is there, and put that as part of one of the IP cores onto the OpenCL compiler, and see how that works.
What is the prediction mechanism, the algorithm? Like, what is it looking at? And is it a statistical thing? Like, how did you do it?
So it is a heuristic-based algorithm. So sort of what was motivated from was how you have performance counters in hardware. So those things, hardware counters actually track what is going on as the hardware runs. So in a similar sort of fashion, when we schedule the tilt schedule onto the target architecture, as the schedule is running, we track how many bank conflicts or how much the FUs are not being reused. If you could schedule an FU operation on a certain cycle, but because of this resource being unavailable, we cannot schedule this. So because of those heuristics.
Need some context for that. So the input to the predictor is the software program that's going to be compiled on the tilt.
The input to the predictor is the application itself. So you have the software kernel.
But,
yes.
Yes. But you jumped into talking about the scheduling. But you need to back up and tell me, for every possible architecture, you create a schedule and then.
No.
Okay.
So
can you give me the context before you give me the detail?
Yeah. So the input to the predictor is the software kernel. So a software description of the kernel, and the tilt architectural configuration that you want to.
No, you're predicting the best tilt
yes.
thing. So
yes.
There's lots of tilts, lots of tilt architectures, right?
Yes. So the input to the predictor is your configuration, and what I meant to say was a constrained set of parameters on what knobs you can turn for your tilt architecture. Because the tilt architecture is theoretically infinite. You want to be able to constrain the design space to a certain space, right? So in that space, what we look at is, as you're generating, we start with the basic tilt core with everything that is needed and nothing else. Very small implementation. And we look at, as you're generating the tilt schedule, we look at what are some of the hardware constraints or that limited the throughput. And by increasing this knob or increasing this resource, for example, adding another functional unit, because we see if that throughput improved, and if that did, then that was a good choice, and you can move on to something else.
So you're executing the schedule on a base thing in a base architecture. You see a bottleneck, you change the base architecture, then you re-execute.
Yeah, we regenerate the tilt schedule, yes.
Regenerate the schedule.
To see if the throughput improved.
And you can tell the throughput by looking directly at the schedule?
There's no branches, so yes.
No, so it's just a straight computation, I see. Interesting.
Go ahead.
Can you flip to that slide where you are comparing the performance of the 5 benchmarks against Altera's OpenCL 2? Can you flip to that slide for a second? You kind of blaze through and
sorry for the, I think it's the.
that's fine.
Tell me when to stop. This one?
This one.
Okay.
So, what was this graph show? Compute density. Okay, so that would mean that you're measuring everything with respect to what OpenCL is able to produce, and the way you obtain the reference value is throughput divided by area. So
we have the throughput and area results in the paper as well, but I wanted to focus on this.
yeah, so I was actually curious about it. So
Sure.
for the benchmarks that you're presenting, were you able to match the throughput that OpenCL produces? And if so, how much? Obviously, it costs you
more area. Yeah.
More area. What about things like clock frequency? Was that?
The clock frequency is essentially around the same. So they're all over 200 megahertz. They're all within this ballpark of 20 or 40 megahertz, not gigahertz.
Is that true for the OpenCL implementation and tilt? Or are you saying all of these benchmarks?
No, so between the tilt design and the equivalent OpenCL HLS design, I'm talking about the clock frequency. The clock frequency between benchmarks differ more. There's more variance.
Okay, so then the next question is, what would you have to do to your tilt architecture to bring it on par with OpenCL?
So I think it will go against the design paradigm of what tilt tries to do, because if you look at the tilt architecture, the main design paradigm, or the main thing that we thought of when we designed this, was reusing the functional units. And the way you do that with is having an area functional units, scratch-fed multi-ported memory, right? And crossbars that will allow you to reuse that set of resources, right? So if you try to change it into a more OpenCL-like architecture, we have to completely rethink how the tilt architecture is designed, right? Instead of these crossbars, we need to make it spread it out into a more pipeline kind of thing. And I think it will. I think the tilt architecture is like one set, kind of on one side of the spectrum, and the OpenCL HLS is on another, which is one of the interesting reasons we thought of comparing it as well.
So maybe you could just highlight, like, well, why do you choose an architecture like this? Like, what is the key thing this gives you?
Mm-hmm. So the key thing this gives you is area. So if you want to, for example, there's a lot of different things that you want to do on the FPGA, right? You could possibly think of putting this in if there's like a computation that can happen on its own, right? And can talk to some other resource memory units. It could be DDR memory or something else. And so that would be the best fit, I think, personally.
I think that's true. I think there's one other key thing. I mean, you basically, this is part of the answer to Tom's question, I guess, is that you don't want to give up the software programmability.
Yes,
right?
that's the other thing.
And
but that's
what
also
you're
a given
saying
as
is
well.
To, in your opinion, to equal the performance of OpenCL's synthesis straight to a hardware pipeline, you would probably have to give up the software programmability. Like,
yes.
You don't have to.
Yes.
Is that correct?
Yes.
I don't have to do it either.
Because the other advantage is that you do not need to re-instantiate the hardware if you want to. If you have a change in the application kernel. The only reason you need to resynthesize your design is for two reasons. First, if you introduce a new functional unit that was not already instantiated, and the second reason is if you want to tune those kernel changes onto that architecture. Otherwise, you can just have that overlay architecture instantiated once and reprogram it as many times as you want.
Okay, so before Vaughn's question, I have one more.
Sure.
So as you both mentioned, you do not want to give up software programmability, which makes a lot of sense. So the next question would be, the results that you're presenting, are they the best you could get without giving up software programmability, or can you do better? A, choice A. So. Can you prove that?
Which one is A?
The first thing you mentioned.
The first was, this is as good as you can do? Is that what you're saying?
Or
you can do better?
It, by the way.
You should say what A is. I don't know what the answer is.
The former, not the latter.
Well, that doesn't happen.
The person who asked you doesn't know what the answer is either.
What I'm really asking you is, you've got a set of results that are based on an architecture that is software programmable.
Exactly.
My question is, without giving up that programmability, is it possible on any of the benchmarks to achieve better results or not?
Without changing the tilt architecture,
No. Without giving up software programmability.
Without giving up software programmability, I think I'm not sure about the tilt architecture itself, but the answer is yes, because there's lots of other things you can do. For example, change how the crossbar connectivity works without having to change your underlying software programmability.
Okay, so just to rephrase what you're saying, at least the way I'm hearing it, what you're saying is that it is still possible to further improve the throughput of your system without giving up the
software
programmability,
yeah.
But you have to make some changes
to the underlying architecture. Yes.
Operates.
Yes.
Do you have any thoughts about what those improvements may be? I don't actually ask for data because I don't expect you to have it, but
I actually do have data on this, but one interesting thing is, so the person who made the tilt architecture originally, who was Colin, so the crossbars essentially are fully connected, right, to all the banks within the memory. So you can, at every cycle, you can each functional unit can communicate with each bank. So that is, what we have seen is that is not necessary. So we can, instead of a fully connected network, such as the crossbar, we can use something else like BANIS, Bennett's network or class network. We do have numbers on that, and that does improve the throughput a little bit, about 10 or so percent. 10, 15%, I think. Just by changing the connectivity of the crossbars of how the functional units connect and talk to the memory system. This one.
I think the key difference there is you're using multicast, right? So
Yeah.
Yes, exactly.
Could have talked to anything else, and multicast just turns out to not be very useful.
Exactly. In this context, at least. Yes.
So Tilt is a VLIW processor.
Sure.
It runs instructions
Uh-huh.
on multiple FUs.
Pardon?
It runs instructions on FUs.
Mm-hmm.
Do you have a sense of what instructions per clock cycle the processor is achieving on your benchmark?
I have this number as well. I can't recall at the top of my head.
Well, first thing is, what's the typical number of FUs in a single core? Is it 1, 3, 10, 100?
So it depends on the benchmark, but let's say if you have 5 different FU types, usually you have usually the densest architecture has up to 3 of those of that same FU, right? So if you have a add sub instruction, right, the densest configuration will most definitely or most likely will not have more than 3 of those functional units. We find that any more than
So you're
3
saying that a typical Tilt core would have about 5 FUs?
Sure, yeah.
Okay.
Mhm.
Okay, I got lost.
Why did you add 2 to those 3?
He said 3 of the same type, so 2 of another type.
Ah,
It sounded like what he was describing as there are 5 FUs and 3 of them are the same type.
So that is actually remarkable that you, it is easier to say 5, right?
Easier to say 5.
I actually also, I think Henry's guess is probably approximately correct, but yeah, 5 is the more succinct way to say number of FUs. So,
I forgot
is
what
it
the rest
5?
You're looking for
You just
I was
confused.
looking for IPC.
Yeah.
You're looking for instruction. I have this number as well, but
Okay, I see. The
After-
instruction
after
per
looking
cycle, is it closer to 0.1, 1, or 5?
closer to 5.
So you get almost 100% utilization of your 5 FUs.
Mm-hmm. Oh, you're talking about that.
In a single core, there are 5 FUs.
I can give you the FU utilization numbers. It's about, for the densest architectures, it's about 60 to 70%. So I can give you that exact number. I can't give you the IPC because it's like sometimes 5.4, 2.4.
And are there stalls because of waiting for DDR?
So for these particular benchmarks, there were no stalls.
Because your memory fetcher is
Exactly,
fetching
it's
fast
good enough, yes.
Great, good timing if that's the end of questions. Thank you very much, Rafat.
Yep.